Hi everybody, Mrs. Danielson here, and today we're going to talk about the binomial theorem. Binomial theorem is pretty cool. It's a major time saver and pretty easy to learn. So let's go ahead and get started on the binomial theorem. I think you're going to like it as much as I do. What we're talking about when we're talking about the binomial theorem is if I take a binomial, a plus b to the n, whatever exponent n is. In the past, you've had to multiply a plus b times a plus b to expand it. So most of the time it's going to be like a plus b squared or a plus b cubed. But if it was bigger than that, let's say a plus b to the sixth, how would you have done that, right? In the past, you would have had to do a plus b times a plus b 6 times, right? A plus b times a plus b times a plus b, you get it, right? It would have been so much work. We wouldn't have even had to go there. But now we're going to use the binomial theorem to expand a plus b to any exponent without having to do all those times, right? And the way we're going to do that is by taking advantage of some patterns that actually emerge when you expand a binomial. So let's just look at a few examples. We're going to go ahead and just write them out, and then you're going to be able to see the patterns that emerge. So a plus b to the first power is just a plus b. But if we took a plus b squared, we'd get a squared plus 2ab plus b squared. And we're just going to list a few of these out so that we can see the patterns. If we had cubed, it would be a cubed plus 3a squared b plus 3ab squared plus b cubed. Let's do one or two more. Let's say we had to the fourth, right? Then that would be a to the fourth plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the fourth. That's probably good enough for now. All right, so what patterns do we start to see when we start to expand these binomials? Well, the first pattern, let's list these out here. The first one is that there are n plus 1 terms in the expansion. With a to the n being the first term, and b to the n being the last. Right, so what that means is like take that last one, a plus b to the fourth. That means there are 5 terms in that expansion, n plus 1, right? So 1, 2, 3, 4, 5 terms, n plus 1. The first term being a to the n, the last one being b to the n. Okay, so that's the first pattern that emerges, n plus 1 terms in any of the expansions. Okay, the second pattern that we're going to pay attention to here is that the exponents of a decrease by 1 from left to right, and the exponents of b increase by 1 from left to right. Okay, so what we're saying there is, again, let's just take that bottom one as an example. The exponent for a is 4, 3, 2, 1, and then 0 would be the last one, right? It's decreasing as we go. B, on the other hand, would be 0 in the first term, and then 1, 2, 3, and 4, increasing from left to right. Okay, and then our last pattern is that the sum of the exponents of any term have to add up to n. Okay, so if I look at, say, this term right here, n in this case is 4, so they have to add up to 4, right? This one right here would be 3 plus 1, which is 4. 3 and 1, 4. Okay, if you add all the exponents of one term, they need to add up to n, or in this case, 4. Okay, so those are our 3 patterns that we can see to have developed just in that short list of expansions that we did right there above it. Okay, so here's how that's going to help us. Okay, let's say we want to expand a plus b to the 5th. Right, and we don't want to do a plus b times a plus b times a plus b times a plus b times a plus b. That's so much work, okay? We are just going to use the patterns we just came up with, right? So we know that the a exponent starts at 5 and then decreases as we go, okay? So we're going to have an a to the 5th, an a to the 4th, an a cubed, an a squared, an a to the 1, and then an a to the 0, which is 1. Okay, and then the b, right? The first one's b to the 0, which is 1, so we don't have to write it. And then we have a b to the 1st, a b squared, a b to the 4th. Oh, that's a b to the 3rd, a b to the 4th, and then a b to the 5th. Okay, pretty easy so far, right? Okay, now the only thing that this equation is missing is it's missing coefficients, right? There have to be some coefficients in that equation. Okay, so how do we know what the coefficients are? Okay, the coefficients in that equation are going to come from Pascal's triangle, which we just barely learned about. Okay, in Pascal's triangle, row 0 is 1. Again, this is Pascal's triangle. And below that, we have 2 1s. And then we just add the 2 numbers above it. Okay, outside edges are 1. Outside edges are 1. 1 and 2 is 3. Okay, the next row would be 1 and 1. 1 plus 3 is 4. 3 and 3 is 6. Okay, for this one, we need row 5. Okay, so we need one more row. 1 and 1. This would be 5. 4 and 6 is 10. Okay, now I know that's row 5 because this number right here is a 5. Okay, so that's as far as I need to go to be able to do this particular expansion. Okay, so my coefficients are 1, 5, 10, 10, 5, and 1. And there we have it. Our binomial expansion for a plus b to the 5th power. Right, I could probably clean that up, make it look a little prettier. Right, I don't have to put the 1. Right, so a to the 5th plus 5, a to the 4th, b, I don't have to write the 1 there either, plus 10a cubed b squared, plus 10a squared b cubed, plus 5, I don't have to put the 1, plus b to the 5th. And that's my binomial expansion for a plus b to the 5th. The easy way, right, using the binomial theorem. Okay, excellent. Okay, all right. So we're usually probably not going to do a binomial expansion that is a plus b. Okay, usually it's going to be something else. Okay, so let's start switching it up a little bit. Okay, let's say one of our numbers is negative instead. Okay, now usually what I recommend when it's something that's different than a plus b, it's usually good to just kind of start with an a plus b. Find out what that expansion is first, and then substitute. Okay, so in this case, what is the binomial expansion of a plus b to the 4th? Right, it's a squared, a squared, a to the 4th, and then a cubed. Let's give ourselves a little more room here. A squared, an e to the first, right? And then a b squared, a b cubed, and a b to the fourth. And let's just grab our coefficients from that Pascal's triangle right up above there, right? It's 1, 4, 6, 4, and 1. All right, so a plus b to the fourth is a to the fourth plus 4. I'm just going to clean it up a little bit, make my spacing a little more pleasing. All right, plus 4ab cubed plus b to the fourth. All right, so the only thing that's different between a plus b to the fourth and v minus w to the fourth is going to be my letters, right? Plus the fact that b is actually going to be a negative. So I'm going to now substitute in there. For my a, I want a v to the fourth. So everywhere I see an a, I'm putting a v. And my b is negative w. So I'm just going to go through, do some substituting for a and b. V, w. Okay, and then just substitute. I mean, just simplify. Okay, so v to the fourth is the same, but right here I've got a negative w times 4v cubed. So that's going to be negative 4v cubed w. Okay, the next one is negative w squared. So that's going to be positive w squared times 6v squared, w squared, like that. Okay, all right. The next one is negative w cubed. So that's going to be a negative w cubed, resulting in negative 4vw cubed. And the next one is positive because it's to the fourth power. All right, and that would be your answer. Okay, so you just substitute in the v and the negative w and simplify. Okay, and that would be your answer. Okay, still easier than if you had to do it the old way. Okay, all right. Now I want to do one more. Okay, stepping it up in difficulty just a smidge. Okay, we're going to do 2 minus 3x to the fifth. Okay, what is that? I would use the same method as this last problem, where first I would find out what is a plus b to the fifth, get the binomial expansion on that first, and then substitute in 2 for a and negative 3x for b. Okay, so first we're going to expand a plus b to the fifth, right? That's a to the fifth, and a to the fourth, and a cubed, a squared, a to the first, right, and then an a to the 0, which is 1. Okay, a b to the 0, b squared, b cubed, b to the fourth, b to the fifth. Okay, and then our coefficients, right, which is off of our Pascal's triangle right there. 1, 5, 10, 10, 5 and 1. 1, 5, 10, 10, 5 and 1. We just won't write the 1 there. We don't need to do that. And there's our binomial expansion for a plus b to the fifth. Wow, that was easy. So easy, right? Oh, we didn't have to do all those a plus b times a plus b. Okay, now we're just going to substitute in 2 for a and negative 3x for b, and then simplify. All right, so that's going to be 2 to the fifth plus 5 times 2 to the fourth times negative 3x plus 10 times 2 cubed times negative 3x squared plus 10 times 2 squared times negative 3x cubed plus 5 times 2 times negative 3x to the 4th plus negative 3x to the 5th. Barely squishing it in there. Okay, and now just simplify. Okay, so 2 to the 5th is 32. Okay, 2 to the 4th times 5 times negative 3x. That's going to give you negative 240x. Okay, 2 cubed times 10 times negative 3 squared, which is 9, times x squared is negative 720x squared. Okay, the next one, negative 3 cubed, that's negative 27 times 4 times 10 times x cubed. Okay, negative 3 to the 4th power times 10 would be 810 x to the 4th. And negative 3 to the 5th is negative 243 x to the 5th. And that is it. That is 2 minus 3x to the 5th, the easy way using binomial expansion. Okay, that's it. So great. What a fun tool. Thanks everybody for watching, and